Good morning or good afternoon, everybody, depending whatever is your time frame. And welcome back to this course on statistical mechanics for chemistry and material scientists. This is essentially course for equilibrium statistical mechanics, and we have been studying of late polymer, the physical chemistry of polymer, and the picture that you see on the slide in front of you is that of Paul Flory, who played an enormous role in fashioning this subject. Before I proceed further, let me tell you this course will be a little different from the earlier courses which were recorded in Bombay IIT studio. This one is because of the coronavirus epidemic. I am recording it from home, so you won't be able to see me, but rest of the things will be okay. You'll be able to see the slides and you'll be able to follow. And what I'll do, go to revise the course, first 5-10 minutes of what I did in the last class, and then we will go into do some new things. This might be a bit of a longish class, but and there will be some expressions and derivations, but we will not derive the lengthy equations, but I'll sketch the derivation, and you will find the derivations in my book on the same title of the course. And there are two other books I want to bring to your attention. One is the book by Paul Flory on principles of polymer chemistry, and there is book by Dijan, Pierre Dijan, on scaling concepts in polymer science. These two books together just will be more than enough. And as I was telling you about Paul Flory, who created almost the much of what we know about polymer science today, and he is rightfully called the father of polymer chemistry. He got Nobel Prize in 1974. And there are many things that he did in polymer, and he did both theory and experiment, and which is remarkable because he did theory at a very high level. Paul Flory was born in 1910 in a place in Illinois near Chicago, and he graduated from Ohio State University and then joined industry, and from industry he then moved to Cornell University, and at the Cornell, where he did much of his pioneer work, and he also published his book from the Cornell University. Now, the next slide, I give the plan of the lecture. So this is something we did in the last lecture, polymer size end-to-end distribution, and with a random walk analogy. It takes you to Gaussian distribution. And then we started polymer thermodynamics. We'll do a little bit more of polymer thermodynamics, and we'll talk two kinds of transitions in polymer, two kinds of phase transition. One is a Sol-Gel transition. By the reason of doing it is that it bears close similarity to Mayer's theory of condensation, gas to liquid transition. It is a kind of a clustering transition. Here Sol means solution of monomers. The monomers connect together to form a branched polymer, and which is then become a highly viscous solution. It's a very important industrial process, and is used widely. As I have told you already, that polymer is one of the most important part of our daily life, and from textile to rubber to many things that we use every day. For example, your diode in many things is organic semiconductor is a polymer, MEHPPV. So and many of these things are made by some kind of a sol-gel transition. So it's an important thing. So we'll just go through this in a rather simple fashion without the blackboard. I'll be more qualitative, but I'll show the equations. So in the third slide, I briefly do the overview that a polymer that we think are millions and millions of connected monomers. Monomers themselves are somewhat complex molecules. and we polymerize them, means we add these monomers together, and many of the fast applications of so polymer, since is a large system with a large number of monomers, it's a natural playground of statistical mechanics. And one of the important property of this polymer is end-to-end distribution function of a polymer, which is expressed in terms of number of monomers, and which is n and between the monomers. We'll talk of effective interaction, solvent effect, and we'll talk of several other remarkable properties and some observations that we have got. In the next day, we shoot the random coil polymer chain, and this is a kind of a ribbon diagram, and you can see the two open ends of the polymer, and in between that there is a long contour where the connected chain connected of monomers is kind of, it takes a random zigzag fashion, and that's why it is called a random walk. One of the reason that it is so random lies in the chemistry, in the basic chemistry, and that is when I start with A0 to A1, the beginning to the first bond between A0 and A1, that bond, many of these are C-C single bond, carbon-carbon single bond, and they can take this tetrahedral geometry. That means it can rotate in 3 dimensions. So that bond can take many directions. And then the next one, so you join one bond which already can rotate in many directions to another bond which again can take many directions. So between, by the time I have 10 some bonds connected and each of them take many configurations, we already have a huge number of configuration space, that means rotational configuration space that this polymer can enjoy. And that's a very important property of the polymer. This huge number of configuration space, the configuration degrees of freedom that a polymer enjoys because of this rotational flexibility or rotational degrees of freedom. So these different polymer that arise because of the rotational degrees of freedom, sometimes there is a preference of certain orientations, and then one talk of rotational isomer. This is a term which was coined by Russian scientist Wolkenstein, and which Fleury also used later. So in this slide that we are showing, that we are starting one, then we have these different bonds, and then bonds are going, and last is the other ball at AN is the red ball. So this is the ping pong diagram, and in order to get end-to-end distance, that be from A1 to AN, from one into another end, that is called R, the universal notation R, and that is what we will calculate now. And that end-to-end vector R can be easily seen is nothing but sum of all these small vectors, and these are small bond vectors. And each of the bond vector has a lot of independence from other because of the rotational degree of freedom. So these bonds arise have the because of the vectorial nature. The length could be the same, that is the bond length L, but they are vector. So because of the vectorial nature of the bond and the rotational degrees of freedom, R is a random number, and that probability distribution of R is a subject of great interest, and that is the one which is a Gaussian distribution, as we discussed last class and also will discuss today. Okay, now this is we discussed, but let us discuss again. This is essentially a rough caricature of a polymer, which is a ribbon. We call this as a ribbon diagram, and you can see there end-to-end distribution going on here. And these end-to-end distribution is, you can see from one end to the other end, that because of the large intervening contour going from one end to the other end, which can take many configurations. In a certain way, it reminds you of a rope, or a dangling or dancing rope or snake. And this ability to take many configurations determine the end-to-end distribution. So roughly the size of the polymer, when you say size of a polymer, we essentially talk of two things. How on the average, how far is my end? It's average quantity. What is the average distance? And since it's a random quantity, that average is a mean square. And this is a very close close analogy. It's random walk. So as if it has the monomer to monomer distance is almost as a random walk. And we will discuss this now immediately a little bit. Extremely important to realize that the end-to-end distribution, along with the end-to-end distribution, to giving you the size of a polymer, there is one more quantity, it's called radius of gyration. Radius of gyration is nothing but the kind of moment of inertia. That means you take the position and MIRI square and sum over, and that gives you also a called RG. That also gives you a measure of the size. And these two quantities, the mean square end-to-end distribution size and the radius of gyration, are very closely connected to each other. They have the same size, same dependence on number of monomers, but they have some numerical factor which make them different from each other. So we can use either radius of gyration or mean square, root mean square end-to-end distribution as the A. This is what I was telling, that we will be discussing a little bit of the random walk scenario, and then go to A1, A2, A3, and then go over and go to endpoint. That two endpoints are given by two red spheres. And one important thing to know here, that when I go from A0 to A1 and A1 to A2, then A0 to A1 bond vector can rotate and can take a large number of orientations. This is not quite 360 degrees because there is some steric hindrance posed by a molecular architecture, but it is fairly flexible. That means it can take many orientations. So now you consider that you are orienting one from the other and then to other. So by the time you have just 8 or 10 monomers connected, just a 10 mark, already you can see a huge number of configurations that can this polymer can take. It is extremely important to realize the inherent huge flexibility of a polymer, the huge number of internal degrees of freedom, the configurational degree of freedom that a polymer enjoys. And that is very important part of its properties, which Fleury realized very early, along with Wolkenstein. And Wolkenstein coined the name rotational isomer. These multiple configurations that polymer gets was recognized by both these two giants of polymer chemistry. So now if I want to go to end-to-end distance, we call it R, then you realize that this is nothing but the sum of the vector. Just like random walk, I want to go one place to another place to finally place. Then where I go finally, if I number of steps, then I add up the steps in a vector way. And that's why vector is important, depending on orientation. That's why orientation is so important. So you can now see the end-to-end distance, both the vector and the scalar, is a dynamic quantity and is also random, hugely random, because you see it now in one position, then if you are in a solution polymer, in a little later you will see in a different position. So it is completely moving around, coiling and uncoiling and things like that. So the way to say that we try to have an idea of this is what appears to be extremely important, extremely complicated, but it turns out to be not complicated. Not only not complicated, it is a beautiful universality
that Florey-Falkenstein realized, and later was, I told you, has been enormously exploited in physics community, where polymer physics is a big subject now. So this is the sum we get, and now we have to get a distribution of this R and R vector. As I told you, this R is a stochastic quantity, it's a random quantity. Now the way to do that then is many ways it can be done. It can be just applied. You don't have to do central limit theorem. We can apply to random walk. But central limit theorem gives a very easy way access. It's a very well-known theorem, and I discussed last time that if I have a quantity S, which is the sum of n number of random quantities, and then this when I sum it up, that sum is a Gaussian distribution. That's called central limit theorem. I don't want to spend too much time on that, but it's a very robust theorem. As I told you last time, mathematicians are not given to give this kind of name, fundamental theorem, central limit theorem. That's not. There is more in physics and chemistry. We give grandiose name like theory of everything or a very great thing, but not mathematicians. They're very conservative people. So when the central limit theorem, it is really central theorem of probability theory. That if I have n number of random variables, I add it up, then that goes over to a Gaussian distribution with a mean u, and the mean is very easy to understand in this case because it is rotating, and so you can easily convince yourself the mean would be 0, but then everything holds on to the width of the distribution, which is the standard deviation, which gives the size. Because if I now want to get the size, then I have to get the average R squared, second moment of this distribution. Okay, so this is one little bit on central limit theorem. You can find it on Google. Do it in internet. You'll find huge amount of things on central limit theorem. But main thing is that n to be large. But as I told you, by 10, 12. You already have fairly good Gaussian distribution. This is one of the things we always use in computer to generate a Gaussian distribution. We generate 12 random numbers, we add them up, and the sum becomes the Gaussian, and that we use in computer. One of the thing is that this is to be mutually uncorrelated. That means from one step to another, from monomer 1 to monomer 2 and monomer 2 to 3. So 1 to 2 and 2 to 3, and they have to be independent, and that is guaranteed by the rotational degree of freedom. So then one can further quantify these things by taking the R along Z axis, then you project it on the R and you get L cos theta I, and you take R end-to-end distance as Z axis and then project on that. Then L cos L is the length, L is the monomer length or bond length. And theta is the one that orientation gives you. That's what gives you the randomness. So since theta is random, cos theta is random, and now we can do R squared, and I can evaluate the cos theta with 0 to pi, and I can evaluate the R square average, and that's exactly done here. That when you do that averaging, because I and J is these are on bonds. I and J are I'm doing on bonds. So one bond and another bond is uncorrelated. So then I have cos theta ij is just one sum, because otherwise so then we get n there, and so R square is NL square. So it's a beautiful result, a really beautiful result. So it tells you mean square is NL square. So for that I don't need the Gaussian distribution. For this I don't need the central limit theorem. But I need the central limit theorem to get the distribution of R. And I can get that they are also through random walk. So there are 2 points here. A, that mean square, R square is scaling as root over n, which is extremely important result because that gives you the size of the polymer. And then comes the distribution. So the distribution is Gaussian, as I said here. There is a R square factor here. Here, I am asking what is the probability that there is a little bit problem here that n should be capital N on both this side or small n on both the two sides. But you will see these mistakes are not in the book, but there are a little bit mistakes here and there in the slides, but which you go back and look. So the end-to-end distance R is for capital NR should be there, then this is distribution. The probability that you have the end within a distance R, and because of the spherical symmetry of the system, so it is in a volume element, in a shell, that shell is 4 pi R square. So at a position R, it is exponential minus 3R square by 2NL square plus the normalization. But you have to multiply by 4 pi R square. Okay. So this is this quantity that this n to the power, that this result n to the power half, and that size, then you can do the radius of gyration this way, and exactly same way you can derive. It is also the second moment. You just change your central of your coordinate system, and you again see that it is RG is root over n. So, but basic central result is the following, that probability distribution is Gaussian with 3 exponential minus 3R square 2NL square. And so standard deviation or the width of the distribution scale as root over n. And that is what we call size. So as I told you before, radius of gyration, which gives a good measure of the size of the polymer, and the mean square end-to-end distribution, they are essentially the same thing. And so as the numbers, as I told you already, a polymer is millions and millions of monomers. That means n is upward of 10 to the power 7, say, or 10 to the power 8. Now, if L is couple of angstrom, then you can imagine that n to the power n to the power half, 10 to the power 8, it's 10 to the power 4. So if this is 2 angstrom, then 10,000 into 2 angstrom is essentially 20,000 angstrom. So radius of gyration is 20,000 angstrom. That is essentially roughly a huge sphere. So you can understand this monster polymer is sitting in solution. And they are not one polymer like that. There are many polymers. So these monsters, 10,000, 20,000 angstrom with radius, nearly spherical things, are suspended in solution. So that's what makes the polymer solution thermodynamics so interesting. It is not a binary mixture. It is a binary mixture, but it's a binary mixture where one guy is 10,000 times larger than the other guy. It is very important to get a sense of number, that what makes polymer so unique, that polymer solution, you have this big floating around, and many of them will precipitate if they are not preferably solvated. And we see these situations in proteins. In a folded protein is almost, again, a globular protein is nearly spherical, but they are of course much smaller. They are a few hundred, many of them, and so they are much smaller. But even then, protein solution is a very interesting area. So polymer solution stands out from protein solution. Many times we say they are the same. It is not quite the same. Polymer solution is, the polymers are much bigger quantities. Though we do map a protein into a polymer and use the language of polymer science or polymer chemistry to explain proteins. Okay, now this was done by Falkenstein and Florey. Now another beautiful calculation that Florey did, and this is just a gem. Florey now said, okay, I wanted to find it in D dimension. He of course did it in 3 dimension, but he also did it for D dimension. He said, how do I find the size of a polymer in a D dimension? He said, okay, he has to now say, okay, as I told you that this polymer is a monster, it's a big thing. So there is a end-to-end distribution, there is an interaction between monomers. So interaction between monomers depends on the concentration of the monomers. So what is the size of the monomer? Size of the monomer R to the power D in D dimension, R cube in 3 dimension, R square in 2 dimension. Now, if that is so, and if monomer has a volume B, then I can consider that a concentration of monomer Why I need the concentration of monomer? Because I need the density. Why I need the density? I need the density so that I can consider interaction. Why I need density to consider interaction? Because when the monomers are next to each other, they are close to each other, they are interacting, and they are far from each other, they are not interacting. So interaction energy is proportional to square of the concentration. Now, where did you see such logic before? That where the interaction energy is square square of the density or concentration. Current class, I would have asked you, and then I would have pestered you to come up with the answer, and you ultimately I would have got the answer out of you. But since I cannot do it now, let me tell you the answer in Van der Waals theory. In Van der Waals theory, there is a repulsive term P plus then V minus NV and P plus A by V square, N square by V square. That's where exactly the same logic Van der Waals used. That in order to interact, both the two molecules should be in a small volume element. And in this, what is the probability of them volume element? If they are independent of each other, then one monomer to be there is the concentration or density. Second monomer is also concentration. So it should be product of the. Okay. So that's why concentration is so important, which is showed here in N by RT, which is the concentration. Okay. Now, in case of chain obeying, we know in this case, in this RT, if it is fluoride polymer or Gaussian polymer, or that is called ideal chain, then R goes to B to the power N to the power. In that case, the number of monomer contacts can be very easily found out to be N phi square by because there are N number of monomer, so total number of, so you have a contact, one polymer, one monomer in contact with the other is this N1 minus D by 2 you can find for the earlier one, and however, N is this 2 minus D by 2. Okay. So this is now what we are going to. So this is we'll continue with the logic in a minute. Before that, let me consider the little bit now. I want to understand polymer interaction in solution. As I told you, it is suspended in solution. On many occasions, typically the solvent is considered a good solvent. Polymer likes the solvent, then the polymer gets so well, and then a lot of solvent molecules come inside. So it is kind of a porous thing. So polymer has within itself, in its size, R to the power D, in that volume element, it has all these polymer molecules. So the way we sometimes talk of that, okay, if polymer, if the monomer polymer like each other, then there will be more monomer inside. Then effectively, polymer and polymer is not going to like each other. However, if the polymer monomer of the polymer does not like a solvent molecule, then they will push these water molecules out. And as a result, I'll find effectively, because the solvent molecules will put an effective force, then the two monomers attract each other. So I have a situation, it is all devised by Chlorine, where depending on the quality of the solvent, good solvent or bad solvent, two monomers effectively, there's an effective interaction, like each other or they don't like each other. So this effective interaction is the one which plays a very important role, because if I don't want to talk of the solvent, I'll talk later, but not in the beginning. So now I'll do something without that. So this is this. I was saying, in a good solvent, the solvent molecules come in and the polymer gets swelled. In a bad solvent, however, it collapses. And there is actually a transition between the, you can change the quality of the solvent by changing temperature. And at certain temperature, this transition takes place, which is called theta temperature. Okay, so this is the effect of solvent is very important, and you have it in the. You will get this. You will get the slides along with the talk, and you can look at it and see of the revision.